So we're going to go over a few basics here this morning before we leave the Holtzman Express, and go over some logistics and go over an overview of what we're going to be seeing on the field trip. But before we do any of that, I just want you to glance back this way. Don't look at the sun. Look down below the sun, and you can see some mountains. All right, we're going to be studying the underlying structure of those mountains today. Now, way off there in the distance, the most distant mountains you can see there, sort of right underneath the sun, that's the Blue Ridge, all right? You guys drove through the Blue Ridge this morning on your way out here, and we're not going to be paying attention to the geology of the Blue Ridge today. This mountain right here, to the right of the telephone poles and to the left of the McDonald's sign, that's Massanutten Mountain. That's the northern tip of Massanutten Mountain right there. You can see there's one little knob that has a little radio tower on it, or a TV tower. That's Signal Knob. Signal Knob was used as a signaling station during the American Civil War because it has a vantage point that allows you to see from this side of the valley over to the other side of the valley around the tip of Massanutten Mountain. So it's sort of a good place to send signals over great distances pretty efficiently. Okay, this is a topographic map of the region. If you can't see it, reposition yourself. You have 10 seconds. So check it out. Here's the Blue Ridge. You can see that it's got a very different craggy sort of feel to it than the Valley Ridge, which has all these valleys and all these ridges, all right? So they're separated along here by a thrust fault that's taken these Blue Ridge rocks, which originally started off like over here by Annandale. And then when Africa smashed into North America during the Allegheny and orogeny, it snapped them off and it shoved them up into the west, where they climbed up on top of younger rocks. So these here are Mesoproterozoic and Neoproterozoic. These here are Paleozoic. So these are like 1 billion years old to 500 million years old, and these are like 500 million to 350 million or so. So these are much younger. And you can see that there's this really distinctive shape to Massanutten Mountain, where it's this long skinny ridge that basically wraps around a long skinny valley, all right? Almost like a canoe in terms of its shape, all right? Our field trip today is to examine that setup. So if we were to take a giant samurai sword and slice through the middle of Massanutten Mountain and the Fort Valley and the Shenandoah Valley and the Page Valley and the Blue Ridge, it would look something like this. All right? You guys can drop that so you can see. All right? You can see that overall, the structure of this region is a giant downturned fold. All right? And this giant downturned fold is named for Massanutten Mountain. It's called the Massanutten Synclinorium, all right? An overall syncline that has smaller scale anticlines and synclines superimposed on it, all right? So the Massanutten Synclinorium. Here's the Blue Ridge over in the east. You can see the thrust fault that's brought the Blue Ridge up over these younger these younger Paleozoic rocks, all right? And then you can see how you've got the same rock layers over here right in front of the Blue Ridge that you have over here in the Shenandoah Valley, all right? The older rocks are going to be located on the fringes of the Page Valley or the Shenandoah Valley, and they get younger as you work your way towards the middle, right? Superposition says the youngest is on top, all right? Plate tectonics can mess with that, but in an otherwise undisturbed stack, that holds true. So we're going to start off today by looking at some of these limestones that are at the base of the sequence here. These are going to be Cambrian age limestones. At our second stop, we're going to see a transition from limestone into increasingly clay-rich strata, shales, all right? And there's even going to be this red stuff here is basically volcanic ash, all right? The shale is going to get coarser and become sandier, so that by the time we get to stop number 3, we're going to be in Greywacky. That's what the GW stands for here. All right. Then we're going to stop and have lunch. After lunch, stop number 4. Is that a 4? Yeah. Okay, good. Stop number 4 is going to be the Massanutten Sandstone. this very resistant rock unit that's quartz rich and pokes out of the landscape as mountains. All right. If you look over that way, you see another mountain over there. That's North Mountain, and that is also underlain by the Massanutten sandstone, although they call it the Tuscarora sandstone over there. Same thing though. Then after that, we're gonna go into the Fort Valley, and we're gonna see some limestones that overlie that, and then some shales that, actually let me go ahead and put this here. Some shales that overlie that with some more volcanic ash in them. All right? Then at the very end of the day, hopefully we will have time. Is that a 7? Yeah. Good. We're going to take a hike into the heart of Little Crease Mountain. And Little Crease Mountain is basically a small anticline that's been superimposed on the larger Massanutten Synclinorium. All right? And if we hike into the guts of this mountain, we're going to see little anticlines inside it. And they're exactly person size. So what we're going to see then is sort of this, oh, that didn't work out well. Here, let's try it again. There we go. We're going to see this change from nice, clean carbonate sediment into dirty sediment with the onset of the Taconian orogeny. Then we're going to see the same thing, going from nice, clean carbonate sediment into dirty sediment with the onset of the Acadian orogeny. And then we're going to see all this nice flat-lying sedimentary record folded up as a result of the third and final phase of Appalachian mountain building, the Alleghenian orogeny. So we're going to see the sedimentary signatures of 2 episodes of mountain building, and we're going to see the structural signature of a third later episode of mountain building.
Interesting.
Questions? So the volcanic ash is called bentonite. Is that what you're fishing for? Yeah. So bentonite, it's named after a spot in Missouri where it was first described, Fort Benton, and that was named for Thomas Hart Benton, U.S. Senator and avid proponent of westward expansion, manifest destiny. So that's where the name comes from. But basically, bentonite is just volcanic ash that's rotted. Volcanic ash, when it's fresh out of a volcano, is made out of tiny little shards of glass. And that glass is not chemically stable because it's disorganized on the atomic level. And over time, it converts to this clay called bentonite. You are on Route 55, and you are just before the bridge over Mulberry Run. That road right there where we parked is called Back Road. Like my professor tweaked his back this morning, so his lower back hurts. Back Road. The rock unit that we're looking at here is called the Conococheague Formation. All right? I want you guys to check out the Conococheague Formation, figure out what its deal is. Robin, do you have any equipment that you're willing to loan them? Okay, Robin has some acid. If you feel like dropping some acid, go to Robin, get some, and then you can use that in your investigations. All right, you guys have been trained. You've been spending months now thinking about rocks and structures, depositional settings. Go to it. Make me proud.
Do you mean like those? Like the ones that in between? Right here?
Okay, those things? Yep. So who has some acid?
Me.
Great. One thing you'll notice is that this gray stuff tends to fizz pretty well, but this lighter gray stuff tends not to. Yeah. All right?
Yeah.
Unless you grind it up and make a powder,
Is it
in which case
dolostone?
you might get a little bit. Yes, this is dolostone.
Okay.
So this stuff is dolostone, 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 dolostone. All right? And then this stuff is limestone. So there's been a partial replacement of some of the limestone with dolostone. All right? So a little bit of extra magnesium ions and fluids that are circulating in this stuff after deposition, and you end up getting that that replacement. But there's something else that's really worth spotting right here.
Hey, that is a stromatolite.
I told you.
Oh, yes.
So here's the bed, and it's been cross-sectioned, and then within the bed you've got these little beds that are at an angle. So it's... All right, there's some cross-bedding right here. All right, from that cross-bedding you can read current direction, right? Yes. Cross-bedding's formed under a current, so the current must have been flowing in this direction from left to right, right? Are these right side up or upside down? Because cross-bedding looks different right side up versus upside down. Right side up, yep. Because the cross beds are tangential to the main bed at the bottom, and they are truncated at the top.
Hey, there's a
that?
Is that
Very
a
good.
stromatolite?
Yeah.
All right.
It's like in there, right?
So check that out. Skylar has spotted a stromatolite. Do you guys see that stromatolite doming upward there?
Yeah.
And if you go over this way, you can see some others doming up.
That's crazy.
Yeah, it's calcium. All right. So we've seen some stromatolites here. That's cool because that's our first fossil of the day, right? We like fossils. Here's some fossil slime. Woo! Woo! Fossil microbial mats. Yeah. Pretty great. Okay, guys. So why should we care about that stromatolite? Oh, cool. Raccoon skull. Great. Collect that for me. I want to give that to my kid. Unless you want to keep it. Okay, we got no cars for a second. Why do we care about these stromatolites?
It tells us.
Okay, it tells us it was marine, but we
Yeah.
probably already figured that out on the basis of the fact that it's limestone, right?
Yeah.
So there must be some greater significance. Okay, I hear lots of people talking. I hear lots of cars going by.
Shallow water.
Shallow water. Great. So this must be shallow ocean. All right? It's got to be shallow because what do stromatolites need in order to live? Light. All right? They need light to photosynthesize. Because as you guys deduced in lab this past week, the life habit of stromatolites is that they are autotrophic. They are photosynthetic microbial mats that grow up towards the sun. So there's a real nice indication that these waters that deposited the Conococheague formation must have been really shallow. Did anyone else see any other evidence of shallowness? Ooids!
Yes.
Who saw ooids?
I did.
All right. So back there at the beginning, there were a couple of boulders sitting in the grass and they had ooids in them. Remember, ooids are little chemically deposited spheres of calcite that form in shallow wave depths where the waves jostle them back and forth. Good. Anything else that tells us about the shallow conditions? Okay, so you've got some banding, some fine banding. All right, so that indicates relatively calm depositional conditions, right? All right. So calm depositional conditions could be consistent with shallow conditions, or it could be consistent with deep conditions. All it says is that it's calm, though. Is there anything else that suggests shallow? Okay, lighter color. Right, this isn't a particularly dark colored rock, although at this point in the day and with its shadow, it's hard to calibrate. But good. All right, it does tend to have this sort of dove gray color. What's the only other primary sedimentary structure we've seen here?
Cross-bedding.
Cross-bedding. Cross-bedding is caused by currents, right? And currents, while they're not unique to shallow environments, they're more common in shallow environments than they are in great depths, all right? So the cross-bedding is consistent with the shallow environment of deposition. Our next stop will be a lot quieter than this one. So we can sum up by saying this: the oldest rock we're going to see today, the Conococheague Formation, was deposited under shallow water marine conditions, all right? It's around 500 million years old. It's around 500 million years old. So that's after the Cambrian explosion. It's in the Cambrian, all right? And was there any mountain building happening at this time? No. What would this look like if there had been mountain building happening adjacent to this depositional setting?
Way higher.
Yeah.
It'd be way higher?
It'd be uplifted.
It dropped down?
There would be folds.
Okay, well, it is folded, all right? The rock layers here are not horizontal. They're dipping at an angle. And that's part of this large-scale Massanutten Synclinorium,
Yeah.
all right? It's part of a big fold. But that's not a 500 million-year-old fold. That's a much more recent fold that took the original Conococheague flat-lying, originally horizontal sedimentary layers and then folded them, all right? What would the sedimentary rock look like? What would the sediments deposited here look like if there was mountain building happening? Would they be pure limestone and dolostone?
They would.
No,
it would
they'd
be,
have a lot of other crap in them,
yeah.
right?
Yeah.
They'd have clay,
So
they'd have
deep,
sand,
yeah.
they'd have pebbles coming off of those rising mountains
Yeah.
next door. We don't see any of that here,
Yeah.
all right? There's no volcanic ash here. So this suggests that these were deposited under passive margin conditions.
Small cave.
There's a small cave right there?
Where?
Hale, show us the cave.
Oh.
Woodchucks are groundhogs that have the capability of chucking wood.
Question is how fast.
No, the question is how much.
How
All right,
much?
guys, we got a little cave here. Is that surprising or is that to be expected?
Expected.
Yeah, limestone tends to dissolve under the weak acid of rainwater. All right? It has carbon dioxide dissolved in it, making carbonic acid, soaks into the ground, makes caves. This area, the Shenandoah Valley and the Page Valley, where we have these Cambrian and Ordovician age limestones, they're shot through with caves. There are caves everywhere around here. Skyline Caverns, Shenandoah Caverns, Luray Caverns. All of those are examples of caves, commercial caves, etched into this soluble rock. All right? Now, one of the neat things that happens when you dissolve away all the limestone is you tend to get left with the stuff that can't dissolve, the clay. So there is a little bit of clay in this rock, all right? And the stuff that's left to line the floor of the cave is this sticky red clay, all right? It's red because any iron in it is getting oxidized now, today. And it's clay because that's basically this very fine stuff that hasn't dissolved in the cave excavation process.
I can't actually tell how deep it goes, honestly.
Why don't you crawl in there and find out?
I can get my flashlight out.
Yeah, you won't get too far. Most of these caves are quite small. Very few of them are quite large. But, there are some large ones around.
I think it goes pretty far back.
Good. All right. Who can really impress me with their geological vocabulary by telling me what the kind of topography is that's dominated by caves, collapsed caves called sinkholes, disappearing streams? Karst. Good. And who can tell me the fancy name for the structures that form through deposition inside a cave?
Stalactites.
Stalactites are an example, but not. What's the general category? Robin. Speleothems. All right, one more chance to redeem yourself. What is the rock type that makes up speleothems? Travertine. Very good, Mitch. That's 2 out of 3 for you. You win a notebook. Oh, wait, I gave you a notebook last time. Never mind. You don't win a notebook. All right, so travertine is important. Travertine is freshwater limestone. It makes the stalactites and the stalagmites of caves, as well as all the other cool cave formations like cave pearls and cave bacon. But travertine can also be deposited not in caves, but on the surface of the earth. We are going to go to a spot where you can see some travertine being deposited today in a stream. You can see we've gotten closer to Massanutten Mountain here. You can see Signal Knob with its distinctive little communications tower on it there. That's the northern end of Massanutten Mountain. So we're getting closer, and that means that we're moving up in the stratigraphic section, right? Because remember that the oldest layers are on the outside of the fold. As we head towards the core of the fold, we're moving up in stratigraphic succession, which means we're moving forward in time. And that's useful, because unless we're somebody like Christopher Nolan or Quentin Tarantino, we like telling stories from the beginning toward the end, right? So so we're looking here at another rock unit. Now, it's not actually the next one in the sequence. Here's a stratigraphic column that covers some of the rock units we'll be seeing today. We started off at stop number 1 with the Conococheague Formation. You can see there were some other limestone formations that preceded that we didn't bother with. All right. We also skipped over the Beekmantown Formation, but you just drove through it back there. Between where we stopped and looked at the travertine and this bridge is mostly Beekmantown. All right. We're looking here at the Newmarket Formation, named for Newmarket, Virginia.
So is that where we are now?
No. Great. Thank you, Betty. Where we are right now is we are on Fisher's Hill. Specifically, this little creek right here is called Tumbling Run. All right. And this is called the Tumbling Run Outcrop, or the Tumbling Run section. So if you go on in geology and someday you're like Randy Warren here, and you're an old pro at this, and you're talking with other geology students, you're like, oh, have you seen the succession at Tumbling Run? They'll be like, oh yeah, I went there on one of my Georgia State field classes. Or, you know, when I was at the University of Michigan, we came down and looked at those rocks. This is a classic Appalachian section right here. All right, so Tumbling Run. And Tumbling Run is really cool because it shows not one, not two, but 3 formations for the price of 1 stop, all right? So after the New Market is the Lincolnshire Formation, and on top of the Lincolnshire is the Edinburgh Formation. We're not in Scotland. This is not Edinburgh. This is Edinburgh. You're in Virginia, all right? So this is the Edinburgh Formation, also named for a town just south of here, Edinburgh, Virginia. So, New Market here, then Lincolnshire, then Edinburgh as we walk downhill. Now we're walking downhill, so you might think, oh, downhill, we're going down in the section. But look, the strata here are dipping more steeply than the hill. So you'd actually be walking up through the stratigraphic section, walking forward in time as you walk that way. Capisce?
Yeah.
All right, molto bene.
Real good.
As Randy will tell you, that means very good.
Mm-hmm.
We've got this sequence here where the big deal, the reason that we bother coming here is that it shows us the sedimentary influence of the Taconian orogeny starting. So we start off here with these bright gray New Market Formation limestones. They're fairly massive, they're fairly light colored, and then as we head down through the section, we're going to see that change, okay? So the other thing you'll notice about these is they're fairly fine grained. So as we walk along here, we'll cross the boundary into the next formation up called the Lincolnshire Formation. And you'll know we've crossed that boundary because there's a small disconformity there, all right? And suddenly the strata go from being sort of massive and fine-grained to being much more coarse, and that coarseness is cut into these fine-grained layers. And then they get to be sort of thinly banded. So let's walk downhill, and you guys tell me where you think you see the change, and I'll let you know if you're right or if you're absolutely totally wrong. Lars, come put your eyeball on this. Here's where you can see the contact between the top of the Lincolnshire and the bottom, the top of the New Market and the bottom of the Lincolnshire. This contact right here. And you can trace that up. You can see it really prominently right there. Do you see it?
Yeah.
All right. So it goes from fine to relatively coarse. Yep, you can trace it. It's about 7 or 8 inches up in that cliff up there. Yeah, it's a little squiggly, which is what you expect for a disconformity, right? Where you've got flat-lying sedimentary layers on top of other flat-lying sedimentary layers. Okay, so New Market, nice to have met you. We're going to cruise on ahead into the Lincolnshire. It starts right here. If you didn't get a good look at it, look for the blue paint here. That marks the contact. In many places on this outcrop, you'll see these little white stripes running through it. And these white stripes are calcite veins. They are essentially healed fractures in the limestone. So limestone had been turned to rock. It was no longer squishy lime mud. And then that rock broke, and then fluids squirted into that fracture, and those fluids carried with them dissolved calcite, and they sealed the fracture shut with pure calcite, which is not light gray in color because it has no clay, no organic component. It's pure white, all right? So these are healed fractures. And the age of those fractures is impossible to date directly. We can't do isotopic dating on calcite. It's not one of our handful of isotopically datable minerals. But we know that it must be after the rock has been turned to rock, after the mud deposit's been turned to rock. And one thing that was really stressful for these rocks was the Alleghanian orogeny. So probably these fractures are part of the Alleghanian orogeny, a structural signature of the Alleghanian orogeny. And I'll show you a more compelling example of that further down here. Now, there's something extra here that we haven't seen yet. So we're in the Lincolnshire Formation at this point. So here's some nice limestone, and here's something that looks a little different. Do you guys see that?
Oh yeah.
Or right there?
Isn't that cool?
Or right there? Or right there? Do you see those things?
Mm-hmm.
Who has acid?
I do.
Okay, Lars, step up. You got your
there's
acid.
more of it.
Lars, put some acid right here. Fizz?
Yep.
Okay, now put some acid right here.
Nope. No fish.
Oh, no fizz. So that is not calcite. All right. These little things right here are chert. All right. They're little nodules of dark colored chert. Does anyone know the fancy geology name for dark colored chert? Flint. All right. So
Oh,
these are little
wow.
flint nodules in here. Flint is made of silica. All right. It's not calcite. So you need to have some source of silica in the rocks. And one possibility for that is sponges. All right. You guys have learned about sponges in last week's lectures. Sponges either can make their little support structures out of calcite or silica. But most organisms that we find in the Paleozoic made them out of calcite. There were very few that made them out of silica. Sponges are one of the few candidates available. Nowadays, we got things like radiolaria and diatoms that make skeletal material out of silica, but that wasn't the case in the Paleozoic. So, it may be that there were some siliceous sponges living in these waters, and then when they were buried, their silica dissolved, traveled around through the rock, and ended up reforming as these dark-colored nodules in the rock. If you were to go into a cave and you see little bumps sticking out of the wall, chances are they're going to be little chert nodules like this, all right? Because that stuff doesn't dissolve, all right? The surrounding limestone would be stripped away, but the chert nodules would not. And why would you care about chert nodules, say, if you were living in this area 600 years ago?
For fire, yeah.
Fire? Sure, you could strike them against steel and make fire.
Arrow making.
Arrow making, right.
Yeah.
So one of the nice things about flint is it breaks with a conchoidal fracture. And if you have two conchoidal fractures that intersect, they make a really nice sharp cutting edge. So they're very useful for making tools. And because it's actual cryptocrystalline quartz rather than just volcanic glass, it holds its edge much better than, say, obsidian would. All right, this is harder than obsidian. To take a look at this section right here. There's a nice big bed here. Wow, look at that chert nodule, huge. There's a nice big bed here, and it's full of fossils. See how many you can identify.
5.
You didn't even look at them.
About tree fitty.
Tree fitting.
Oh, I see one.
Where?
Right there.
Oh, yeah.
I think this one's one too. Yeah. And right over there. All of these are just a bunch of shells. Bunch of shells, yeah.
I think that's number 8.
Interesting.
Okay, who thinks they identified one of those invertebrate organisms there?
Well, there's a whole
David.
bunch down here.
What's your spot?
Oh, it's not. Sorry. Shells. They're like little.
You can't just give me shells. You've
Sorry.
gone through an invertebrate paleontology lab.
Let's see.
Bivalves?
Yeah.
Possible.
Really?
Brachiopods, yes. There are many, many. They also contain everybody's favorite trilobites.
Oh,
All right? But the trilobites here have, they have a different skeletal material than do most of these other critters. Trilobite skeletons are made out of chitin, which is like what crab skeletons are made out of today. And one of the interesting things about the silica that was flowing through these rocks and depositing these flint nodules is that silica turned the chitin of the trilobite skeleton to silica. So you can actually take samples of this rock and bring them home and put them in full-strength hydrochloric acid, and it'll dissolve away the whole rock, and you'll be left with mud, like that red clay that we saw coming out of Hale's cave back there at the first spot. And in that mud will be little silicified trilobite bits and pieces. All right? So what you're looking at here is the tail end of a trilobite. This is a little cheek armored horn kind of thing coming off the trilobite. This is a either a head plate or a tail plate of a trilobite called an agnostid, which was planktonic. It floated like a little castanet in the water. And over here, this one's my favorite because you can see a little bit of the trilobite eye. All right, they had compound eyes like flies. So this one over here shows those little compound eyelets. All right, and those were actually, when they were around, the actual eye was made out of single crystals of calcite that conduct light very efficiently down the c-axis of the calcite crystal.
Professor, what's the bones made out of again? What?
Chitin.
Chitin.
Chitin, the skeletal material, not bones, but the skeletal material of trilobites is made out of chitin, C-H-I-T-I-N, which is the same thing that
'Cause, yeah, I see, yeah. lobsters
lobsters and crabs have their skeletons made out of. These,
These,
I don't know if you can see this, but these these images were made by a former student of mine who had a great name, Anastasia Bogosian Scissors. Love that name. And she was an honors student in my historical geology class, and she helped dissolve these things away. I'm looking down here at the bottom of this placard. 10 years ago. 10 years ago. And bringing students to this outcrop for more than a decade, evidently. So, anyhow, these are neat rocks. So not only is this sort of a cool outcrop for telling the Appalachian geology story, but it's really useful for people who study trilobites. There's a guy who's the curator of paleontology at the Natural History Museum in London named Richard Forty. He's a trilobite expert, and he's written books about trilobites, and in those books you'll hear this outcrop referenced, because he came here and collected and dissolved out these beautifully preserved trilobite fossils. A little hard to see here, but look at this cliff right up here above my hand. Do you see lots of little calcite veins in there?
Yeah.
Do you notice how they're all parallel to one another in a band going this way? And there's another parallel band going up that way?
Yes.
Yeah. So that particular pattern, where you've got a bunch of short little veins like that, that's the sort of pattern that people who study the deformation of rocks like to pay attention to, because you can read the stress directions pretty cleanly off of that. In the interest of time, I'm not really going to go into it right now, but I will just sort of emphasize that this is probably more of this Alleghanian deformation of these layers. So when these layers were deposited, by the way, we're into the Ordovician period at this point, they were deposited horizontally in relatively shallow water, all right? Nowadays, we find them tilted and they're cracked, okay? And that tilting and that cracking probably both happened during the Alleghanian. So we're sort of seeing two things at once here. Have you guys ever heard the term palimpsest?
No.
Historians like this term because way back in the day, people couldn't afford a lot of fancy papyrus, right? So they'd use the papyrus for writing down one thing, and then later on, they'd scrape away at the ink, and then they'd write over it again, kind of like erasing a whiteboard. And you could still see kind of what was written there before. That's called palimpsest. This is sort of a palimpsest view of geologic history. We've got sort of one story written in the sequence of sedimentary layers and another story written in their orientation and their fractures. Kevin is risking his life here for the extraction of some interesting material.
Good luck, Kevin.
Wait.
All right. Everybody say thank you, Kevin.
Thank you, Kevin.
All right. So there's this crumbly sort of yellow stuff that Kevin has just extracted. See how there's this layer here that's much more easily weathered out, all right? And so it's recessed into the face of the outcrop. That's full of this yellow crumbly stuff. This is bentonite, all right? This is what used to be volcanic ash and then turned to clay. And it's got this sort of characteristic yellowish tan color, and it's very crumbly, all right? So it readily weathers away, more rapidly than even the limestone. And remember, the limestone can be dissolved by rainwater. So this stuff is pretty weak, pretty unstable, all right? So this is bentonite. And bentonite is what again?
Volcanic ash.
Volcanic ash. So what do you need to make volcanoes?
Rock.
Subduction, yeah, I mean, actually there's many ways to make volcanoes, but one of the best ways is subduction, all right? So subduction is something that occurs at plate boundaries. If you have volcanic ash being deposited here, that suggests that there was a volcano nearby. If there was a volcano nearby, then perhaps there was a plate boundary nearby. You guys follow that?
Yep.
All right.
Oh.
So this layer of bentonite, so there's a big one that's right up here that's about maybe a foot thick, but then there's several others like here and here. The first of those bentonite layers is the base of the Edinburgh Formation. So you've now left the Lincolnshire Formation and you're in the Edinburgh Formation. So if we put the stratigraphic column back up, you can see it there as the next layer up in the sequence. Notice how in the stratigraphic column I've kind of color-coded it as being a little bit darker. All right?
This is the Edinburgh now.
So the Edinburgh Formation has a lot more clay in it. And that allows it to split because there's some sort of clay-rich layers here between the limestones into these separate layers. So this isn't sort of massive anymore. It's much more obviously layered. And some of those layers are these bentonite layers. Now, one of the neat things about these bentonite layers is people have said, hey, there's a great big thick bentonite layer here. Let's figure out how old it is. And then they went and they sifted through it for zircons, and they found that it was 454 million years old. And it turns out that that's interesting because in Europe, there's also a really big 454 million year old bentonite. And so people thought, holy cow, check this out. There's this single volcanic ash layer that stretches across Europe and North America, all right? So this must have been one heck of an eruption. And so they could calculate how much material was erupted by measuring how thick these layers are and what area they covered, and multiplying the thickness by the area gives you the volume. And they came up with a number that was something like 1,100 cubic kilometers of ash erupted in this volcanic eruption. 1,100 cubic kilometers. That's a lot of cubic kilometers. A cubic kilometer is a big volume, right? It's a box that measures a kilometer on each side. So then imagine 1,100 of those. When Mount St. Helens in the Cascade Range erupted in 1980, it erupted 1 cubic kilometer. All right? So this would have been a really massive volcanic eruption.
Yeah.
Around what time did this happen?
454 million years ago. Okay? Now the problem with that was that somebody recently went and they did geochemical fingerprinting on the ash. So they basically measured trace elements in the ash. They measured iron, manganese, and magnesium, and they plotted them for about 300 European samples and about 150 North American samples, and it turns out they made 2 distinct clusters. So on the basis of that detailed examination of the ash, they actually think they weren't the same eruption. They were 2 separate eruptions, each with its own geochemical signature. All right? So even though they happen to occur about the same time, they don't think they were from the same eruption. Still, 2 pretty humongous eruptions.
Just a question from back there. Was the move from the Newmarket to the Lancashire, was that also the move from the
Okay, no. So the Paleozoic includes the Ordovician. Okay? So basically the entire Tumbling Run outcrop here has all been Ordovician. So we left the Cambrian behind when we left the Conococheague. You can see that here with the time scale over on the side here. So the Newmarket is entirely in the Ordovician. Yeah, great. So here's a big limestone slab, right? Basically pure limestone, so it weathers out consistently. This stuff here is limestone alternating with clay-rich layers, shale layers. So you got basically shale, limestone, shale, limestone, shale, limestone, shale, limestone, shale, limestone, shale, and so on. Do you guys see that?
Yeah.
All right. This is actually pretty nice right here because it's all kind of consistently lit. Would make a good photograph.
Oh, I took one. Don't worry, I got it.
So that shale is made out of clay particles. Clay particles don't magically come into existence, all right? They aren't spontaneously generated. Those clay particles had to come from the erosion of some pre-existing rock. Perhaps it was being shoved up by a mountain range. So we've got volcanic ash and we've got clay coming into our system. And the analogy that I would offer you would be, say we're out here, you can feel the breeze blowing over us right now. Imagine suddenly you started to smell a little smoke in that breeze, all right? You might be like, huh, it smells like a fire. And then you might look over that way where the wind is coming from to look for some evidence of smoke, you know, some evidence of fire. Where there's smoke, there's fire, right? So in the same way, this clay-rich layer here and this bentonite layer, these are like sort of whiffs of orogeny, right? They're sort of the first sort of signals that we're getting that an episode of mountain building is starting up somewhere nearby. In this case, it's happening off to the east. How do we know it's happening off to the east? Because we can go off to the east today and we can find rocks like those underneath Washington, D.C. that basically were the roots of these ancient Taconian mountains that were being shoved upward at this time. This subduction zone complex that was being partially melted, and that was these Taconian mountains. That's where this clay was coming from. That's where this volcanic ash was coming from. Yeah?
Yeah.
Good. Nice.
What questions do you have?
Why are they shaped like that?
Why are what shaped like what?
The thing, that one thing.
So these limestones, they tend to weather out, I mean, like most rocks tend to weather out spheroidally if they get a chance. And that's because their edges, if you've got sort of a crisp rectangular edge, there's a lot more surface area on that edge than in the middle of a face. So the edges wear away most rapidly. And even though these haven't been tumbled down a river or anything, they tend to become increasingly spheroidal over time. So spheroidal weathering is the answer.
Okay. What's with the slabs? Like, why are they oriented the way they are?
Okay. So what's with the slabs? Why are they oriented the way they are? Whoops.
Pressure from the.
So this slab basically here is nothing but limestone. There's no shale in it, right? So that means that there was a period of time when the local sedimentary basin was receiving clay to make shale, and then there was a time when it wasn't. All right, so it could be that some mountains got shoved upward, they generated a lot of mud for a while, and then those mountains were worn away, and you had a return to relatively carbonate-dominated deposition. But it doesn't last long, because if you go up above it, there's another shaly layer here, another shaly layer there, another shaly layer there, another shaly layer there, okay? So as we head closer to Massanutten Mountain, we get less and less carbonate and more mud and more sand, okay? But your second part of your question is the orientation, all right? So we got this principle in geology of original horizontality. And if we find rocks in a position other than horizontal, we know that that happened after they were originally deposited, okay? So that orientation is an Alleghanian orientation, all right? If you were to say, follow this layer down into the earth, all right, you'd go underneath Massanutten Mountain, and then you'd come up again on the other side over in the Page Valley in front of the Blue Ridge. You'd pop up there like a gopher, and you'd be like, oh, look at this. It's the same exact rock sequence, except in that case, over there, it gets younger going west. Here, it gets younger going east. But it's a mirror image on either side of Massanutten Mountain.
Cool. What's that white thing?
What's that white thing? Lichen. A little bit of lichen.
I like it.
Run again. And I want to point out the really huge travertine ledges that Tumbling Run is built out. Tumbling Run is fed in part by water that comes out of caves underground. Because that water is coming through the caves, it's chock full of calcite. It flows into Tumbling Run. As it gets agitated by going over a small waterfall, it dumps out its dissolved load of calcite and it makes a travertine deposit. That makes a small waterfall into a medium-sized waterfall. The medium-sized waterfall agitates the water more, and so you end up getting a big waterfall. And so these waterfalls are actually made by modern deposits of travertine that are building up over time. It's pretty cool. That's the youngest rock you're likely to see anytime soon. You want to see a younger rock than that? Go to the Big Island of Hawaii and go to Volcanoes National Park and watch the lava flowing and turning to rock before your very eyes. But those travertine deposits there are probably on the order of thousands of years old, maybe hundreds, definitely nowhere near millions.
Pretty.
Young rocks! What a concept! It's freaking crazy. I met the people who live in this house recently at a party. And I'm coming back here in the summer to go swimming down there.
Hell yeah.
Is it fresh?
I forgot to make the point back there that the color changed progressively as we went through that last outcrop. I picked up a bit of the Newmarket and a bit of the Lincolnshire to kind of make that point. So consider this a spectrum with two data. So you can see that this one is lighter and this one is darker. And as you will recall from our discussion in lecture on Thursday, the thought there is that the North American continent had this volcanic island arc smash into it, and it caused the continent to bow downward, right? So to flex down. And so you ended up getting a deeper basin there. That deeper basin meant that the oxygen levels in the deeper water were lower, and that meant that more organic carbon was preserved, and so the rocks got darker. Everybody with me on that?
Yep.
Robin, come be sea level. Okay. You be sea level here, just right on top of my arm.
Oh, here.
Yeah, just like that.
Okay.
Okay, great. Here come the volcanic islands. Your arm stays put. Your arm stays put. Mine bows down. Do you see how much deeper it got? Look,
Yeah.
we'll rewind. All right. Thank you. So that's why the color gets to be a little bit darker as you go up in the section. The other neat thing though about this sample that I picked up just at random off the ground is it's got actually a pretty nice brachiopod fossil in it. So if you want to see a nice little brack with some fine little ribs, look right there. You can see one. Cute, yeah. That's the word I would use. I mean, you guys were distracted by the kitties, but the brachiopods are much cuter. Okay, gang. So are we closer to or further away from Massanutten Mountain? Closer. All right. You can't see the tower anymore, but that is Signal Knob over there on the left. We are here to see the next unit up in our section here. We're going to look at the Martinsburg Formation. All right, the Martinsburg Formation. And then this is the last rock unit before lunch, and it's the last rock unit before the Massanutten Sandstone, the one that makes up that ridge. Okay? The Martinsburg's really cool because it's completely devoid of calcite. All right? Wow. Which means that the sedimentary signal is completely overwhelmed by not calcite materials, silica, so siliciclastic materials, and that includes mud, and that includes sand. So another way to finish that sentence, the system is totally overwhelmed by mountain building. All right? Sediment coming off of the Taconian Mountains, which are rising to the east. You want to see it?
Of course.
Let's do it.
No fizz, so no calcite. All right? This is our signal that the Taconian orogeny has reached its peak. All right? There are mountains off to the east. They are shedding off scads and scads of mud and sand. That stuff is avalanching down to be deposited here. Does anyone see any primary sedimentary structures here? Crossbedding? Yes, but show me what you think is crossbedding. That's not crossbedding, that's a graded bed. Oh, that's what I'm talking about. Graded bed. And there is crossbedding though right here. You see these delicate little things? So that tells you the current was traveling that way. All right, so if you unfold this, yeah, horizontal will be like that. So the source is that way. Yes, so for those of you who are off there standing on the road far away from the rocks, Kevin has spotted graded bedding and Betty has spotted cross bedding.
No,
here. Other way around. Okay, who cares? All right, they both get credit because they're here, close to the rocks, looking at them, doing what I want them to do. Awesome. Good job, guys. All right, so yes, so we've got a beautiful example of graded bedding here, a slightly less beautiful example of cross bedding, and there's a real nice alternation here between gray sandstones and shale, gray sandstone, shale, shale, gray sandstone with graded bedding. Not really sure what that is. Another graded bed here with cross bedding at the top, more shale, more gray sandstone, more shale. What do we call gray sandstone? Gray wacky. Good job, Mateen. All right, now come look at the rocks. Get in here. Question, what's this called? This thin layering, all right? Lars, do you notice how those thin layers are not really parallel to the beds, but they're almost vertical? That is a deformational signature. So what is this feature that Lars is noticing that seems to cut across bedding? So bedding here is like this, and yet then there's this feature that cuts through the rocks and is oriented upright like this, that overprints particularly the mud-rich layers.
Sorry, I'm stepping on you.
All right, this is cleavage. All right, this is cleavage. All right, so I did say cleavage in class, yeah. So yeah, so this sounds even more inappropriate when we talk about the bedding here as well. So we got bedding and cleavage having an interesting relationship here. So the bedding is relatively steeply dipping, more steeply than what we saw at Tumbling Run, right? And the cleavage is almost vertical here. So the bedding is a primary sedimentary feature, a primary sedimentary structure. The cleavage is a tectonic structure, all right? The bedding here is around 440 million years old. The cleavage here is much younger. It's around 300 million years old. The bedding is a sedimentary signature of the Taconian orogeny. The cleavage is from the Alleghenian orogeny, all right? Again, palimpsest. You should remember palimpsest for the next time you play Scrabble. And somehow there's a lot of letters already on the board because that's more than 7 letters. So never mind. It's just crossword puzzles. It's better for crossword puzzles. P-A-L-I-M-P-S-E-S-T. Yeah, I can't really think of a scenario where you'd have that on the board. Let's cancel the field trip and go play Scrabble. All right, check it out. So gray wacky here, shale, gray wacky, shale, shale, sudden transition to a nice thick gray wacky bed. See how it's coarse at the bottom and it gets finer towards the top? That's a graded bed. All right, here's another one. All right, this one has some nice little cross beds at the top, which tell us that the current was traveling this way. Remember, these graded beds are deposited by turbidity currents, right? And so we can actually read the current travel direction from these cross beds. All right, here's more shale, here's more gray wacky. The shale, however, has this dominant cleavage that overprints it. So is this really shale anymore, or is it slate? Tom, is this shale or is it slate? You answered this right in class the other day, which is why I'm picking on you now. Oh, yeah. Yeah, the answer is yes. All right. Yeah, it is a shale. Yes, it has slatey cleavage, so we could call it either one, shale or slate. All right? But nice graded beds here. Weathering. All right? So this is within a single layer of these turbidity current deposits. So you can see that they are broken into these sort of spear-like shapes up there. It's very distinctive. It's, can you go downwind?
That's just me thinking.
It's very distinctive, and it basically is probably the most recent structure you're going to see here, in that this is something that's forming as these rocks are adjusting to surface conditions now. So that's probably on the order of maybe 1,000, 2,000, 5,000 years old, not older than that. Okay?
Wow.
So it doesn't really tell us too much about the geologic history, but it's basically telling us about these rocks turning back into sediment again, right? So these rocks were shoved up into E world in the Taconian Mountains. They were turned to sediment. They came down and were deposited here as D world. Then the Allegheny and orogeny tilted them up and brought them up to the surface again. Now they're being eroded anew and generating sediments again. Yeah, all that green stuff is lichen. It does, yeah. So lichens are symbiotic relationships between fungi and algae. The fungi are a fungus. They have little hyphae. They wiggle their way into the cracks in the rock, and they generate a little bit of organic acid, which helps break down the rock. About this, all right? So check it out. Can you guys squish off to the side of the road a little bit more? But check this out, guys. Look at these nice big gray wacky deposits. So each one of these big thick beds, and this one is like a full foot thick. This is a single turbidity current deposit, all right? A single deposit of sand and mud to make future gray wacky, all right? Separated by shales from the ones above and below it. So think about all of that material being deposited in one geological instant. Another thing I'll point out here is there's a very gentle little fold here. So if you follow these layers up, they go up, 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 and then they bow out, and then they go up again. And the axis of that fold runs right through here. Do you guys see that? So that's a very small scale fold that's part of this larger regional fold called the Massanutten Synclinorium. But this bone's kind of cool because if this were fossilized and I put it on an exam for you, I'd ask you, is this a body fossil or a trace fossil? And your answer would be?
Body fossil.
Body fossil, clearly, obviously. But if you look closely at it, you'll see it's got little squirrel gnaw marks over it. Or maybe it was this mouse. Because this bone is a nice concentration of calcium. So you'll see lots of little gnaw marks. So it's actually a trace fossil too. What do you guys notice about the orientation of the cleavage here? Like, look right in front of Mitch. What's the cleavage doing?
Very good cleavage.
Very beautiful cleavage over there. What's the orientation of the cleavage? It was almost vertical back there, right?
Slanted. Kind of slanted here.
Slanted.
No, okay, you're looking at the bedding there.
On the side.
All right? So bedding here is like this. All right? Cleavage here is almost horizontal. All right? So that suggests that this cleavage maybe was initially vertical and then got folded over on its side. Now, look at this outcrop right here and tell me what you see.
seen an intrusion of the wood in the
Intrusion of the wood.
erosion, the cross wedging and stuff. You know?
Okay, all right, there's some root wedging, sure.
There you go. There you go.
Try not to see the modern biological stuff.
The colors?
Okay, so Tanya, you are going like this.
Yeah, the little lines that go vertical.
The little lines that go vertical, what are those?
Oh,
Cleavage, good. And what about the lines that go like that? Bedding. Bedding, good.
Would this bedding go underneath and back up underneath the mountain like the other one was?
Yes, totally. Yeah. So this bedding would go down underneath the mountain, come back up like the ones we had talked about earlier. But this is just a beautiful example. I think the best example I've ever seen where you can see the bedding and you can see the cleavage and you're not really sure whether this is a metamorphic rock or a sedimentary rock. All right, it's right there on the boundary between those two because it's breaking out equally along the bedding plane and along the cleavage plane. All right, so here's bedding. All right, see my really detailed diagram of showing bedding?
Oh,
All right,
10 out of 10.
and then we squeeze the bedding from the side. What's going to happen to it? It's going to fold and it's going to cleave, right? And the cleavage is going to go like that. All right? If you've got a syncline, well here, if you've got an anticline and a syncline next door, let's just draw both of them. Your cleavage fan for the anticline spreads out going up and your cleavage fan for the syncline spreads out going down. All right? And so what you're looking at here is something that looks like this, all right? Where you've got the bedding at a shallower angle and the cleavage at a very high angle, a very steep angle, all right? So you guys are looking at a rock that's like this, all right? Where the cleavage and the bedding are intersecting, all right? And you would expect that orientation of the cleavage to fan out and then kind of tilt back this way as you go to the other side of the Synclinorium. Okay, so this is a very small outcrop in the grand scheme of things, but it actually tells us something pretty major about the overall structure of the region, just by paying attention to how the bedding is oriented and how the cleavage is oriented. That's an idea, hi there, that's an idea called Pompelli's rule, all right? The early geologist, I think that's Matt's maybe, Raphael Pompelli, state geologist of Rhode Island, came up with this idea that you could pay attention to small scale structures and you could read regional scale structure out of them if you knew how they related. Welcome to the Fort Valley. You're in the narrowest part of the fort here, up near where Passage Creek comes out of the fort. So once again, the name of this mountain range here is the Massanutten mountain system. All right? The valley in the middle of the Massanutten Mountains is the Fort Valley. And the Fort Valley is drained by Passage Creek, which is this body of water right here behind me. Passage Creek drains the fort, comes out of the Massanutten mountain system right here at a place called Water Lick, and then it flows into the North Fork of the Shenandoah. Massanutten Mountain is held up by this rock that you're sitting on. All right? We're done? This rock is the Massanutten sandstone. All right? It is a quartz sandstone where it's nice and clean, like right here in front of me, and you can see it's white. All right? That's because it's almost nothing but quartz crystals. All right? There are a few conglomerate layers in it. There are a few shale layers, but mostly it's quartz sand. A hell of a lot of quartz sand. Thousands of feet thick. Just around the corner here, you can see up on the ridge line there, it's almost vertical, a place called Buzzard Rocks. And that's a really nice place to go rock climbing. Right here, you can see it's got a moderate incline. All right, so it's not horizontal, but it's not vertical. It's dipping at maybe 30, 35 degrees. All right? You can see the gym is over there trying to get some nice cross-sectional views of it. That's adequate, that's a good thing to do. But it's also cool to look at the bedding plane. One thing you'll see on the bedding plane, like uphill from Jeremy and Mary, are little squiggly shapes. Those are Arthrophycus trace fossils. There are more of them right there as well. Little squiggly things that look almost like a piece of rope, or right here. Look at these. All right? Those little things are trace fossils where some critter was going through the sand prior to it getting turned to sandstone.
What's the location again?
This location is called Passage Creek, specifically Red Hole. All right? This gentleman fly fishing over here is fly fishing in Red Hole. It's a great place to go swimming in the summertime. Just around the corner is Blue Hole, an even better place to go swimming because there's a rope swing there. This Massanutten formation is basically nothing but quartz sand. All right? It's got lots of ripple marks and cross beds that indicate deposition under relatively shallow conditions, and it doesn't really have any mud mixed in with the sand, which suggests it's well processed, all right? So it's been winnowed out, it's well sorted, not like that gray wacky that we saw back there at our last stop before lunch, okay? So basically, remember we talked about bowing the crust down and making this deep basin? Well, we filled that in with the Martinsburg Formation. And now it's being topped off with this huge deposit of quartz sand. So, over here on my little key for understanding this stuff, you can see that the Taconian Orogenes influence has pretty much ceased, and now we're back into passive margin sedimentation. So we got these nice clean quartz sands here, the sort of stuff we might expect to pile up on modern-day Virginia Beach or Ocean City, Maryland. Acetate, lots of quartz sand there. Okay?
Passive margin what?
Passive margin sedimentation. Sediment on a passive, non-active margin. But as before, it's not horizontal, right? Because after this, there's still some more orogeny to go through. We got to dump some more sediment into the system from the Acadian orogeny, and then the very fold that you're sitting on right here is evidence of the Alleghenian orogeny. When all these nice flat layers got folded up into this big syncline, or Synclinorium. Questions? Those are not ripple marks. Those are the traces of crossbeds. That's what crossbeds look like from the top. All right? So you've got a series of crossbeds that are accumulated this way. All right? So the current that deposited this was moving in this direction. If you go over to the side here, you can see some ripples in cross-section as those migrated along, they dump those little layers. So this is the amazing thing. Right here at the head of the mountain, the east limb and the west limb come together. So just around the corner there where that silver car or greenish car just came from, where that black car just came from, the rock layers over there are dipping this way. And so you basically turn around the corner and you go from west dipping rocks to east dipping rocks. Say it louder, Mitch.
Does the river flow out north?
Yes.
Where does
It flows out north, right just around the corner here, where when we were driving in, we went from sort of open farm fields to forest, and then suddenly there were rocks right next to the road. That's where it leaves the mountain system. And it's fascinating there because right through here, this is an incised meander. I mean, it's locked in here. It's not migrating much in either direction. But then right there at that spot, suddenly it just spreads out wide and you get a huge braided river system there. Classic looking braided river system. Yeah, it goes into the North Fork of the Shenandoah. And then just about 3 miles further east to the South Fork. What's this?
Virginia.
Virginia. Very good. It's kind of a funny look at Virginia though, isn't it?
Got a rainbow.
It's a rainbow state. All right. What's going on with that rainbow palette? What are we depicting with all those colors? Six prophecies?
Province.
6 provinces. Oh, okay. Well, but we got a lot more than 6 colors there, don't we?
Not rock.
Elevation, that's a good guess, but this is not showing elevation.
Types of rocks.
Types of rocks, right? These are different formations. All right. So this dot here, what is that? Gosh, I would have thought that was Richmond. Richmond's actually down here. So I don't know what that is. Something on my map. Okay, so check it out. So here's Washington, D.C. Annandale's like about here. This is the Culpeper Basin. Triassic Age Rift Basin. Here's the Blue Ridge. Mitch, you were asking me about Bull Run Mountain. Here's Bull Run Mountain. Here's the Blue Ridge itself. That's the Blue Ridge Synclinorium. All right? And then here is the Massanutten Synclinorium. All right? The purple here, outlining this, is the Massanutten sandstone. And then these blue colors in the middle, and the purple in the middle, that's the Fort Valley. We started out here by Strasburg, and we worked our way in, and we're going to go into the middle of the fort. Can you guys hear me? Yeah. All right, great. Because I'm losing my voice. I wanted to go to some noble purpose. Next week in lab, you guys are going to be looking at geologic maps like this one, and the following week in lab as well. This is a really complicated one. We're going to start you off easy on some of these maps, but you'll learn how to deduce synclines and anticlines even if there's no topographic relief at all. All right? So we'll practice with folds and faults and other stuff next week in lab. All right, other questions? Cross beds, those might be things that we associate with a river system. In other places, though, it has brachiopod fossils, which is not something we'd expect to find in a river. That's something we'd expect to find in the ocean. So probably it was like a braided river system leading into an ocean environment. So maybe we got some beach and some river going on here. Like that. These big obelisks here came out when they excavated for the foundations of that big chicken coop up there. All right? And this is cool because this rock unit doesn't tend to weather out here in the Fort Valley very well because it is soluble and it dissolves away. What do you predict it is?
Limestone.
Limestone. Why don't you go take a close look at it and see if it's a limestone. You've got two outcrops to choose from.
Can we drop the acid?
Which stop is this?
I don't see why not.
This is Seven Fountains Road. Stop
I
number
found
one.
there's brachiopods.
Oh
in there.
wow.
Oh, brachiopods.
Yeah.
Oh yeah, there are.
All over the place.
There are several of them. Yeah. It's just chock full of them. See, look, here's the broken shell, the fill.
Hey, that's cool.
Lots of trace fossils too. Look at these.
Bivalves.
The road is called Seven Fountains Road, and that big lake and that previous property we just passed is Seven Fountains. Yeah, there's a big map right about knee level there. There's a big stromatoporoid. What's that? Is that a coral? Yeah, that's like heliophyllum. Here's another one. Oops, sorry.
Sorry.
I forget, what's the difference between a stromatolite and a stromatoporoid?
Stromatolites are just fossil slimes. Stromatoporoids were basically layered sponges.
Oh.
So stromatoporoids are animals, although they have a similar layered structure.
Okay.
Stroma.
So stromatolite is layered slime.
Okay, guys, so this is a Devonian age limestone. It's the Helderberg group, all right? Or some people would say the Helderberg formation. People who pay attention to limestones tend to divide the group into smaller formations. For our purposes, let's just call it Helderberg. And it's limestone. And the key thing for us to realize is we aren't going to get this limestone if we've got mountain building going on, okay? So in terms of our sedimentary record, we have completely ended the sedimentary record of the Taconian orogeny, the first pulse of Appalachian mountain building. So by this time, by the middle of the Devonian, it's over. And we've gone back to passive margin sedimentation big time. Not only have we got nice mature quartz sandstones, but now we don't even have any quartz sand left. So now it's just basically dead critters raining down to make the sediment. You guys okay with that? Mm-hmm. Okay, good. But remember, there's another phase of Appalachian mountain building that's still to come. What's that next phase, the second one called?
No, the other thing.
Okay, so we've had the Taconian. That's number one. What's the second one? Starts with an A.
Acadian.
No, Allegaine's the third one, which also starts with Acadian. Acadian. So the Acadian orogeny starts just after this. All right? And in fact, by the time we get down to that next little curve in the road there, the Acadian orogeny is fully underway. All right? Do you guys see down there past Jim? There's a shaly outcrop beyond that brown mailbox. That's more shale. All right? And that shale is coming from the erosion of the Acadian mountains. Brianna, do you believe me? Oh, you're very trusting. Unbelievable. All right, let's see if I'm right or not. Let's go.
I love dropping in.
Okay, so look. So check it out. There's a little bit of fizzing from that one layer, but not from this stuff, huh?
Yeah.
All right, so mostly this rock is given over to mud. Very little carbonate. All right?
So what should we label this outcrop?
Okay, great. So the question was, what should we label this outcrop? So that was Helderberg limestone. Now we are in Mahantango Formation shale. Mahantango, sounds like a fancy dance. M-A-H-A-N-T-A-N-G-O. All right, Mahantango. Jim, did you see that yellowish patch of easily eroded stuff there? Yeah. Whoa, Jim has spotted something that looks suspiciously like a bentonite. All right. Oh, that looks pretty crumbly. All right. So a little bit more bentonite here. Yet this is not the same bentonite that we saw before. This is a different bentonite. All right. So this is not the big bentonite. This is the Tioga bentonite. Tioga. All right. Named for a town in New York where it was first described. But this ash layer is not only found in New York. It extends all the way down here, all the way down to Alabama. All right. So it's a very big, regionally extensive ash deposit. Anybody want to see it before I dump it?
No.
Tioga. Well, it's always found in the same stratigraphic position here in the Devonian. And where you've got original zircons left in it, you can date it. All right? So you can't actually directly date the shale, but you can date the ash layer within the shale.
So what is it smashed between?
It's just within the Mahantango Formation. Okay, so what does this tell us? What's our big picture here? No longer passive margin, so what's the opposite of that? Active margin, which is to say mountain building has started again. All right, so now we're getting the sedimentary signature of the Acadian orogeny. All right, so we started off with the Taconian, then we went to passive margin. Actually, we started off with passive, then we went to Taconian, then we went to passive. Now we're into active again with the Acadian orogeny.
Yes.
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 What's the what?
I'm sorry, what did you say again? I was paying attention to the
I said, hi, my name is Callum Bentley. Welcome to Historical Geology.
Hello, Callum Bentley.
Let's go over the syllabus. So, Matt, where did you tune out?
Oh, after you talked about the event tonight, I focused on the event tonight
okay.
more.
All right, so this shale, which includes the bentonite, is called the Mahantango Formation. It's mostly siliciclastic material, silt and clay, and that's coming from the erosion of the Acadian mountains. So this is our first sedimentary indication that the Acadian orogeny has started up. Because remember, just back there where that chicken coop is, that there were passive margin conditions, right? Depositing limestone, all right? So sometime between there and here, the Acadian orogeny turned on. Mountains were raised, those mountains were eroded, they started shedding off mud, silt. That traveled some distance, got deposited here. A volcano went, bah, and then that ash came and got deposited here. Went, bah. Randy, here's your estimate.
So you're thinking in terms of Ocean Island arc volcanoes?
So yeah, so great. Randy's taking it to the next level. So Randy, ask your question again so all these newbies can hear what you have to say.
Well, you've been teaching them, so I would expect them to be already excellent students. But,
Yeah, me too.
Oh.
When we're getting these volcanic ashes, we're probably looking at a volcanic arc that's being pushed ahead of the subduction layer or part of the subduction layer.
So the we are able at this latitude to go and look at the Taconian Island arc because it accreted to North America, had a subduction zone complex in between. All right, so we're talking ophiolites, accretionary wedge, and that's basically our Piedmont. But if we go outboard of that towards the Atlantic Ocean, we come into a little zone called the Chapawamsek terrain, and that's these ancient volcanic island arc rocks that were accreted during the Taconian orogeny.
Okay.
All right. Now, in the Akkadian orogeny, it was a bigger landmass that hit. Okay, a microcontinent, and that was called Avalonia. Avalonia started off on the edge of Africa, rifted away, was out in the Iapetus Ocean for a while, and then it got accreted to the edge of North America. You can see Avalonia if you go to New England. All right. At this latitude, you can't see Avalonia because even though it evidently accreted here, that zone where it accreted is now underneath the coastal plain. So it's buried underneath this blanket of coastal plain sediments and we just can't see it.
Right.
We've got too thin a slice of the Piedmont here. But it is thought to be a microcontinent, and as subduction brought it into conjunction with North America, that subduction would have caused volcanism as well. So there would be a volcanic island arc component to it, but the landmass that got accreted is itself continental crust.
Gotcha.
This is more of our Mahentango formation here. You can see that it's black, all right, which indicates low oxygen depositional conditions. Plenty of clay in here. The other thing that's really distinctive about it is, as a consequence of earth fluid circulating through the rock underground, it's built out these great big concretions. And that's what you guys were looking at in that ditch there. Those big round things.
Yeah.
When they form, they're like perfect ellipsoids, like a sort of squashed sphere kind of shape. And there, if I recall correctly, there's a nice big one right in the middle up here that we can check out. But the lady who I was just talking to there, the daughter of the guy who owns this land, she says that her son, who's 18, is really into geology and he's found a bunch of trilobites here.
Oh wow.
So, so we should maybe keep our eyes peeled for some cool fossils, okay? So let's take maybe 10 minutes to explore around here, just because I've never actually done it, and see what we find.
Tango outcrop too.
Yep. Yeah, but explain the regional structure here with a big syncline that has little synclines and anticlines superimposed on it. So I brought you all the way here into Veach Gap because Veach Gap is where this little creek has cut its way through the heart of one of these mountains. The mountain's called Little Crease Mountain. And Mill Creek has chopped it in half. So that allows us to see into the guts of the mountain, which we wouldn't ordinarily be able to see. So, would you guys be able to recognize an anticline if you saw it?
Yeah.
You think so? All right, I'm gonna let you lead then. I'm gonna let you guys lead. And you guys let me know when you think you see an anticline. Jack, good job. Not obscuring it. Okay, so this is an anticline. Check it out. This is a fold in the Massanutten sandstone. Think about this Massanutten sandstone, how easy it would be to fold it. Can you imagine just picking up a slab of it and sort of putting it over your knee and going, and bending it into a nice fold? No.
Not possible.
Not possible. What would you need to do to make it possible?
Heat and a lot of pressure.
A lot of heat and a lot of confining pressure. Maybe apply the stress very slowly over millions of years, right? Yeah, look at that. I mean, this thing has one limb that is almost parallel to the other limb, all right? I mean, this is a crazy tight fold. It goes up, notice how thick it is in the middle, how thin the limbs are. Yeah, classic. And notice how it's plunging from Jack down to where we are.
Yeah.
Do you see that? The axis of the fold is not horizontal, it's tilted at an angle. That's that same angle that Little Crease Mountain makes on the whole overall landscape.
So it's this over there.
Well, this would sort of dive into the ground over there and it's all covered up. But if you go up the hill, you'll find other examples of it here.
I'm sorry, guys.
You're
Whoa.
literally standing on it. On top of old anticline.
One day I took a hike where I came up here and then I went right up the mountain this way, looking for other outcrops. And I found a few more outcrops of anticlines and I found 2 outcrops of synclines on my way up. But for the most part here, the low spots are filled in with all this breakdown rubble that kind of fills in the low areas. And I took a bunch of photos of that, and if you're interested in seeing them, I put them on my geology blog, Mountain Beltway. So you can check those out if you're interested. What I'm going to do next week is I'm going to go up this side. And I'm going to go up to the top of Little Crease Mountain on this side and go along the crest of it that way to see what I can see. But I haven't been there yet. This is the widest section of each gap down here at the bottom, so you have the most anticlines. As you get up to the top, it gets narrower, and so you get fewer and fewer as you go up. So you're looking at a Silurian age rock here, a sand that was deposited around 400 million years ago, and then it was folded around 300 million years ago, by which time it had already turned to sandstone. Because if this was loose sand, you know, when it was folded, it just would have collapsed. All right, but it was a solid rock at that point in the heart of the Appalachian Mountain Belt.
When was it deposited?
400-ish, Silurian. All right, so I brought you here not to show you another outcrop of Massanutten sandstone, but basically to show you the folds, to sort of tie up that last end of the story that these rocks got severely deformed during Alleghenian deformation. If you're a good, strong rock like the sandstone, you fold. If you're a weak rock like the shale, you cleave.
Bruh. Leave it on for 12 hours. Hey, can I borrow your pencil?
You're not.
That's what you just said. Can I borrow your
That's the Blue Ridge.
I straight sue them.
You're in the wrong
I'll try to get a lot
province.
of money.
He asked about the Catoctin metabasalt.
You know some good shit.
Come on, Randy. This is Valiant Ridge. All we have here are sedimentary rocks and the occasional Eocene intrusive. Okay.
Professor, did you take a gigapan of this?
Sure.
No, did you?
Of course.
You did?
Yes.
Sure.
I don't know. I mean, I'm taking 2,000 gigapans. I know I've showed you a lot, but I haven't showed you all of them. Yeah.
They're good though. They're good.
It is. Yeah, if you're interested, I can. Actually, I think I linked to them in the pre-trip reading. Didn't I have a gigapan?
Right,
Yeah,
you did.
that's
You
a
did.
gigapan.
I saw a couple. Those are so detailed too. I know.
That's the idea.
It just.
Did you just take that with a regular camera?
Yeah, camera like this, a DSLR. But you can take them with a, even an iPhone.
Wow, that's cool. For the gigapan?
Yeah, it's just a bunch of overlapping shots.
Oh.
Okay, other questions about the Valley and Ridge this time?
No, sir. Good trip.
Okay, I actually do have a question. So
Great.
I saw some I don't know if they're quartz intrusions. I know this is a sandstone, but I saw some visible quartz. Is that?
Some vein quartz?
Yeah.
Okay, yeah, sure. So this stuff, when it's being deformed, it cracks, just like the limestone we saw at Tumbling Run. Except here, the fluids that fill those cracks are full of quartz, because they're coming through quartz rock rather than coming through limestone. So you get quartz veins here, calcite veins there.